everybody. One second. Okay. My notes are all over the place. Okay. So any questions before we get started? Okay. So if not, let's pick up where we left off last time. I'm going to add to the start by adding to the notes from last time. So we stated some theorems, and I'll write the proofs today. Okay, so all right, so last time we discussed Hilbert spaces a bit, and we ended by defining what it means to be an orthonormal basis of a Hilbert space. So of an in particular of interest to us is our infinite dimensional Hilbert spaces. We'll see in this class that essentially there's only one of these, where they're all isometric to each other. So what a basis is a an orthonormal family of elements with dense span. So i.e. finite linear combinations of basis elements are dense. And the theorem will prove, which is an abstract theorem about Hilbert spaces, is that we can characterize an orthonormal family being as being a basis in four different equivalent ways. So one, so we stated the following theorem. This first one is this the definition of a that we gave for basis. And then we have three other equivalent definitions. So alternatively, EKs are an orthonormal basis if for each element F and H, such that F paired with EJ for each of the for every J is zero, then F is zero. Three, if I take an element F and H and define F as being the first. So I take F, pair it with EJ for each J through one from N, and then so I write it as a linear combination of the EJs in the following way, up to N. Then this object SNF tends to F in norm as N goes to infinity. And then for the norm of F squared is equal to just taking F, pairing it with all of the elements of the basis, taking absolute value squared and summing. So these are four equivalent characterizations of a family of an orthonormal family being a basis. And okay, so we'll prove this theorem, and then we'll deduce as a corollary. We'll come back to that. We'll come back to this corollary about the Fourier series. Okay, so let's prove the theorem. Okay, so we'll start by proving that one implies two. given f in H, and assume that f paired with EJ is equal to 0 for every j, and we want to show that f is identically 0. Okay, so by assumption, there exists. So so we're assuming I, namely that that linear combinations, finite linear combinations, are of the EKs are dense. So we'll use that assumption. So there exists a Gn is equal to a finite linear combinations of the EKs, such that f minus Gn in norm tends to 0 as n goes to infinity. Right, since these are dense, for every epsilon we can find a finite linear combination of the EJs, so the difference between f and that object is less than epsilon. So we can just take, say, epsilons to be a sequence 1 over n, and then find such GNs like that. Then since f paired with EJ is equal to 0 for every j, this implies that f paired with Gn is equal to 0 for every n, right? Because the GNs are just finite linear combinations. Okay, but now we could just apply Cauchy-Schwarz. So f L2 squared is equal to f paired with f, right? Which, since by the above, is equal to f paired with f minus Gn, right? Because this is equal to 0. And then this is less than or equal to norm of f by the Cauchy-Schwarz inequality times norm of f minus Gn. And this goes to 0 as n goes to infinity. The left-hand side has nothing to do with n, so therefore norm of f, sorry, I shouldn't be writing L2. This is just the norm in the norm given by the inner product in the Hilbert space. Norm of f is equal to 0, but this implies that f is equal to 0. Right, this is one of the characteristics of the Hilbert space. So this means that 1 implies 2 is proved. Let's now prove that 2 implies 3. Let's remember what these are. So 2, again, is that if you have an inner product between f and every element of the set, orthonormal set, then f has to be equal to identically to 0, and we're trying to prove that that this sequence of partial sums converges to f in norm. All right, and this should remind us of the similar argument we gave for Fourier series in the past. So take f and h, SNF is equal to f paired with EJ, j equals 1 to n. So first, we'll show that there exists a G and H such that S and F minus G and norm goes to 0 as n goes to infinity. So we're just going to find something that's a limit, and later we're going to show, and then afterwards we'll show that that limit has to be F. Note F minus SNF is perpendicular to SNF. And if you look way back in your notes, we argued exactly this way with Hilbert spaces, with the Fourier series. Um, all right, so these are perpendicular to each other. And this is by, yeah, so this is true. So therefore, by the Pythagorean theorem, norm of f squared is equal to norm of f minus Sn f squared plus norm of Sn f squared, which is equal to f minus Sn f squared plus the sum from k equals 1 to n of f paired with ek squared. Right, just because SNF is a is this object, right? So since these guys are all orthonormal to each other, when we take norm squared of this, we just get the little L2 sum of these coefficients. All right, so nothing surprising there. And therefore, norm of f squared is bigger than or equal to the sum from k equals 1 to n of f paired with ek squared. And just let n go to infinity and obtain that Bessel's inequality, that norm of f squared. This is called Bessel's inequality. This is very analogous to the proof we gave for Fourier series. Okay, but then this means that this sum on the left converges, right? It's finite, so the sum converges. So k equals 1 to infinity converges. And then therefore, this gives a convergence series. So this is Cauchy in H. It's a Cauchy sequence in metric, right? It's a convergence sequence, hence Cauchy. So since H is complete, there exists a G in H such that we have convergence in norm. So there exists a limiting element. Cauchy hence convergent, so we can find the limiting object. Now, okay, so now the game is to show that note also we haven't used our assumption yet, we haven't used the hypothesis yet. So we're going to use the hypothesis 2 to show that that G has to actually be equal to F. Okay, so fix J. And then for every large enough n, f minus SNF paired with EJ, this is just equal to f paired with EJ minus f paired with EJ. This is equal to 0. As long as n is large enough, right, relative to j, then since we in here we have the exactly this coefficient times EJ, and then paired with EJ we get 1 back again. So this is equal to 0. So therefore, since uh, S and F tends to G um, by the above have, since the above holds for every large enough n, we must have F minus G paired with EJ equals 0 for every J. Right, just by, can see this by triangle inequality, for example. Okay, so therefore, F minus G is equal to 0 by the hypothesis. So therefore, F equals G, and F is equal to, in some sense, in the sense of norm, expressible. Sorry, these should be EKs. EK. In that sense. All right, now for the last implication, or second to last implication. So we want to show that 3 implies 4. Let's take a look at what those were. So we'd like to show the thing we just proved, that 2 implies, namely this, implies 4. But now we're almost there, right? Because we already proved Bessel's inequality. So let's call this star.
Could you do that last part a little slower? I got lost when we were trying to take the limit and get something about G.
Yeah. This very last part where we're trying to show that F is equal to J.
Honestly, I could do with having everything here with starting with fixed J.
Fixed J.
Just having that explained again.
Yeah. Gotcha. Okay, so you're good up to here.
Yeah.
Okay. So we find this. So first we find some limit, right? We show that Sn is a Cauchy sequence. The Hilbert space is complete, so there exists a limiting object.
Hmm.
All right, now we're going to try and show that F has to be equal to J. Has to be equal to G.
Mm-hmm.
Okay, so and we want to use our hypothesis. So where is the hypothesis going to come in? Well, we're going to show F is equal to G as long as we can show this, right? Then we're done, right?
Yeah.
So this is what we're after. This is where we're going to use the hypothesis. So how do we show this thing? Well, first, we prove this by replacing G with SNF. Okay. So why is this thing equal to 0? Well, on the one hand, let me just expand it out. So this is equal to, let me erase this line and I'll expand it out a little bit more carefully. This is just, by expanding it out, this is just F with EJ minus what? Minus the sum from J equals 1 to, let me make this K. K equals 1 to N of the pairing F with EK. EK paired with EJ. Right, I just remember what, sorry, this is a little sloppy. Is that okay? I just expanded out what S and F was and then paired it with EJ. So I get the pairing happens term by term, right? And now note that this is, the EKs are orthogonal, right? Or they're orthonormal. So this thing vanishes unless K is equal to J, right?
Mhm.
And and as long as I take n large enough, I ensure that j is fixed, right? So I just take n large enough so that j appears in this from k equals 1 to n,
So
right?
you just need n to be at least j, is that right?
Exactly.
Okay.
And then I get what I get is f ej minus f ej equals 0,
Oh, okay.
right? So yeah, as long as n is bigger than or equal to j. So this is what I mean by n large enough, which is as long as n is equal to j. But then, okay, for every n bigger than or equal to j, this is true, right? This pairing is just identically equal to 0,
Mhm.
right? Okay, but now if I look at this next pairing that I'm interested in, f minus g, just add and subtract um, SNF here,
Mm.
right? If I add and subtract SNF, I get 0 when I pair SNF with, I take F minus SNF, and then I have SNF minus G, and I can apply Cauchy-Schwarz to that and say that that goes,
Okay.
right?
Yeah, yeah.
Does that make sense?
Yeah.
Maybe I'll just erase. I kind of wrote the same thing twice down here, so I'm gonna just erase that line and do that step real quick. Um, by hypothesis, I can write. And this is, I'll make, um, and this is equal to 0. This is, maybe I'll put absolute values, um, and this is less than or equal to. Um, which in this last term, it can be made arbitrarily small, right?
Yeah. Okay. Got it.
Um, okay. Yeah, thanks, Michael. That was quick. Before. Uh, okay, so that's 2 implies 3. Um, okay, 3 implies 4. Uh, on the one hand, we have Bessel's inequality. So we're trying. Okay, right. So on the one hand, we have Bessel's inequality, um, but in particular, maybe I actually don't even want to. Maybe I don't want to star this. Let me star this. Let me star this. So um, once I have that f minus s in f tends to 0 in norm, I just let n go to infinity turns to 0, and then I recover the thing I want. So let me write that out. By star. Um, this, and then just let n go to infinity above. N goes to infinity. This term goes to 0. Okay, and then finally, 4 implies 1. Okay, so 4 holds. Um, then if 4 holds, then then this is true, right? Uh, um, by the above as well, right? So this is no choice, right? Um, uh, and then since each S and F is a finite, maybe I should write, this is again by star. Since each S and F is a finite linear combination of the EJs, we are done. Because we just approximate F by the S and F. This is completely analogous to the when we proved that trig polynomials were dense, right? Uh, in L2. Okay, in the case of Fourier series. All right, so that does it. And now let me introduce one more concept. Maybe let's see what I want to say. So let me introduce one more concept. So a theorem, and this I won't prove, but notes. The theorem is that any Hilbert space. So we just gave a characterization of an orthonormal set being a basis, and the next theorem is that any Hilbert space has an orthonormal basis. And the proof, which I'll just refer you to the book for this, because I'm actually sure you've seen something like this already in your linear algebra class, and the proof is identical. The proof is just take the countable. So Hilbert spaces, remember, are separable. So just take the countable dense set and do Graham-Schmidt.
I had a quick question about 4 implies 1 before you go on.
Yep.
Where do we use the hypothesis for 4?
For 4, so the hypothesis for 4 is that if I let n go to infinity, if I so I use a hypothesis for 4 together with this equality. So so 4 holds, then this is equal to this, but with n go to infinity.
Oh, okay, right. So the difference goes to 0. Okay.
And then what we can so what we're actually doing is we're saying implies 3 and 3 implies 1, I guess.
Yeah.
Right. So since we have this, then from this equality we could just take the tail. We know this series is convergent. This series is convergent. So therefore the difference between this and the full series goes to 0. And then we're just left with this having no choice but to go to 0 as n goes to infinity.
So would you say it's true that if you're given Bessel's inequality, then it's or that like identity, then it's obvious that like 3 and 4 are equivalent?
Yeah. From
Okay.
here, 3 and 4 are equivalent. Yeah,
Okay.
yeah,
Got
yeah. It's a little. I guess it's kind of silly. It's like it's 4 implies 1 by proving first 4 implies 3,
it.
and then 3 implies 1.
Okay. Thanks.
Can
Yeah.
I ask one question about the theorem you have just said?
This next theorem.
The orthonormal basis. Slightly off topic, but since we have this theorem, are we avoiding axiom of choice? Because we need axiom of choice to prove that any vector space has a basis, but not sure if we do have a Hilbert spaces, can we actually avoid axiom of choice?
Can we avoid axiom of choice?
Well, this isn't quite the same definition of basis as just in linear algebra.
Yeah, we're only asking for basis. We're asking for basis we're asking that uh, we just have a count of a orthonormal family with that's whose finite linear combinations are dense.
Yeah.
So I'm actually not sure where I don't see where we're using axiom of choice in this argument here.
Mhm.
Um, right? Am I wrong? Do we? So is the axiom of choice? So we need to start with something, right? I guess to um, to start Graham-Schmidt, but then Graham-Schmidt's an inductive procedure, right?
Yeah.
I'm sorry, maybe I'm missing something, but I don't think we've used axiom of choice so far, right?
Yeah, I mean, I'm therefore surprised. Like, because proving there is
You
a
need to use wait. I'm sorry. You don't need to use axiom of choice to prove any finite dimensional vector space has a basis, right?
yeah, no,
Um. So uh, so um here here maybe yeah maybe as Michael said or maybe there's some discrepancy in what we're calling basis in each instance. Um.
uh,
So yeah I don't see maybe I glossed over this from the book, but I don't see where I'm using action choice. Um, yeah, I guess because we're only asking for denseness, right?
mhm.
Um, I'm sorry. Is this adequately answering your question? I'm just not sure what the maybe the def maybe what basic what um I think maybe there's just some difference in definition of basis in notion of basis.
Yeah, I guess we have a weaker notion of basis, so we somehow skip
Yeah,
the axiom of choice
yeah,
magically.
yeah, yeah. I think that's the key point. I think um, we there is this built-in finiteness part of our base of in our definition of basis. I think that allows us to avoid this. Um, right? Yeah, and so we're we're really not and what we're saying again about representing f um, by a linear combination of basis elements. What we're really saying is we have convergence of the to f in norm. Um, so I think I think we're avoiding by just being careful about what we mean um, by f equals by this.
Don't you kind of use choice to choose the dense span vectors anyway? Like we know the Hilbert space is separable, so there is some like countable dense subset, but don't you need choice to find that subset to begin with?
Uh,
Sorry, I'm jumping in again, but I think if you just want to make if you just know that something exists, then you can like give it a name. I don't think that requires the axiom of choice,
yeah,
especially if you only want to make like a finite number of choices.
yeah. Yeah, Michael proved this last time in class, the existence of this countable dense subset, right? In fact, he constructed it. Um, right. The proof was a construction. Um, and so like it for L2, sorry, for L2, the proof was a construction for L2. Um, once we have this theorem about bases, um, then we can in fact show that every infinite dimensional Hilbert space is exactly just little L2 by just the same way you identify any finite dimensional vector space with our RD. We just have we have the basis elements now. It just becomes we just have a map into little L2. So with our constructive proof of the countable dense set in L2, and I guess for little L2, the countable dense sets is even easier to attain, right? We just can take the sequences with rational coefficients. I think we don't need to use choice there either. Yeah. Yeah, I don't see the use of axiom of choice at the moment. But please correct me if I'm missing something. But thanks for the question. Yeah, that seems to be right. Okay. Okay. So what one other concept before we go back to the corollary in the beginning about Fourier series was that of a unitary mapping. Which is the following. So if I have two Hilbert spaces, H prime Hilbert spaces, U mapping H to H prime is unitary, or isometric maybe, if one U is linear, two, it's a bijection, and three, it's norm preserving. So U, F, and H prime is equal to the norm of F in H. Okay, so if you can find a unitary mapping between two Hilbert spaces, then they're, for all practical purposes, they're the same Hilbert space. So they're called unitarily equivalent. Oh, Andy, did you resolve our previous discussion?
I'll get it. Yeah, just sending a link.
Okay. Can I ask? Did I misspeak at all, or it seems okay?
No, I think so. The link it has an example of like the difference in bases between thinking of it as like something where span is dense versus like a maximal orthogonal set.
Excellent. Okay. Excellent. Thanks.
Professor, when you begin with the proof, you said that choose a countable dense set, but I guess this requires the axiom of choice. I mean,
I don't think so, right? It's so we can so for example, in the L2 example that we gave, Michael constructed last time a countable dense set.
Mm-hmm.
So in that construction, I don't think it required the axiom of choice. He just built it from scratch using rectangles with rational endpoints,
mm-hmm.
right? So I think even though I say the word choose a rational choose a countable dense set, the choice is axiom choice involves like a choice function for an infinite set.
Yeah.
Right. Here I just meant like there exists such a set, and let's start with that set that we know exists.
Yeah. Okay.
We didn't need to choose a representative or anything like this.
Yeah. Yeah.
So I think
Thank
we
you
I
very
think
much.
it still
Yeah.
avoids it.
Yeah.
But thanks. This is good to flesh out a bit. Okay. So so this is the notion of a unitary mapping. It's a norm preserving bijection, linear norm preserving bijection, and the corollary to the theorem we just stated about finding a basis is that any two infinite dimensional Hilbert spaces are unitarily equivalent. So there, you can always find such a mapping. And the proof, just see the book. I'll refer you to the book, but it just amounts to choosing a basis. It just amounts to finding a basis. Okay. And then, of course, like I think in linear algebra classes, you prove at some point that finite dimensional Hilbert spaces are unitarily equivalent if and only if they have the same dimension, right? Which is again given by just choosing basis. Okay, so let's return to the proof of this capstone from the first part of the class. So here I can, so if I take an L2 function on the torus, then Parsel's identity holds. This map is an isomorphism of Hilbert spaces, and what I mean by here is a unitary mapping in the sense that we just defined between L2 and L2 on the torus and little L2 of Z. And then finally, SNF minus F tends to 0 in norm. So we proved this theorem. We proved a version of this theorem. We proved A and C for this theorem in the case of Riemann integrable functions. The new content is B, but also A and C now in for this wider class of functions, the L2 functions. And so the proof is just this is an orthonormal basis. How do we know this? Well, so the e to the ikx's are an orthonormal basis. Well, we proved, so maybe let me just write the proof of corollary. We proved implies that f is equal for every k, f is equal to 0 last time. So we proved that by showing that the Abel series converges, right? We proved that. So last time we proved, maybe this is here somewhere. I think this is in the previous set of notes. So we proved this theorem for an L1. For L1, and note that in this finite measure space, L2 is contained in L1. So this holds also for L2, for every f in L2. So this is this condition here is one of the 4 equivalent characterizations for having a basis, right? For this being a basis. So sorry, I'm all over the place. So this holds for Fourier series, right? But then we have convergence in norm, and we have this this Parseval's identity here. So we're done. Was that too quick? Okay. All right. So this, in particular, caps off what motivated our study of measure integration in the first place. the onto-ness of this map. Maybe let me just say a few more words about this. So about part B, being an isomorphism. So we want to show that that this map is in fact onto, which is what we're missing for the Riemann integral functions. So proof of corollary. Onto. So just let an be any element be in L2Z, any sequence. Set S and F to be equal to an e to the I n x. This is an L2, right? So it's just a finite linear combination of these ANs. This is just an L2 of T, right? So then AN is an L2. Little L2 implies that this sequence Sn is Cauchy as n go to 0, right? Because if I just take this is an orthonormal family, right? And in fact a basis. So so if I take the entire sum, I just get a convergent sum, right? I get the little L2 norm of the ANs. This tends to 0. Now the key step is, since L2 of T is complete, this goes to for some, and this converges in the sense of L2 for some F in L2 T. So this thing converges some F. So I used there's no F was just something I used in this symbol here, but I'll call the limit F as well for some F in L2. Now just verify that F hat n is equal to an for every n, just using orthogonality. So just by pairing and integrating using these kx's. So that's the this finishes the proof that we have in fact a bijection. So at the beginning of class we proved that the map that the map was 1-to-1, at least etc. So all the stuff from the beginning of class kind of still applies, and then the last missing ingredient is onto, and this is how you prove onto.
Yeah.
Okay.
Sorry. I think Mn should be tends to infinity. I guess
Yeah. Yes.
Issue.
Yes. Thank you. And tend to infinity. Then this tells us that this is Cauchy, and so we can find a limiting object. Okay. Any questions about this last part, which was very fast? Very fast, but also a bit of review. Now just in the right framework. Okay, so the next topic I want to discuss is the Fourier transform. So, and to start, I want to make some analogy with Fourier series a bit. So for Fourier series, we took F, now our now new sophisticated treatment of Fourier series. We took F in L1 of T, um, and um, and then formally, we found that we asked whether f of x can be represented by its Fourier series. F hat n, e to the I, and x. So this formally we have this for L1 functions, where f hat n is equal to 1 over 2 pi, integral minus pi to pi, e to the I, e to the minus I n x, f of x dx. Okay, and we proved the following theorem towards the beginning of class. If f was an A, script A, which was a set with absolutely convergent Fourier series, Fourier coefficients, then we had uniform convergence, right? Then we can recover f from its Fourier coefficients. The sequence f hat n. Right, so that this is the concept of the uniform convergence theorem. We can recover back. So if you just give me the Fourier coefficients of an L1 function, and I know that they're little L1 summable, then I can recover f back again. So by summation, f of x is equal in the sense of uniform convergence effect. All right. So let's now discuss the same problem for functions. So what if f from R to R, or RD to R, which we'll get to in a second. So formally, if I just want to make a formal analogy, I defined f hat of c is just the integral. So to find the Fourier coefficients before were defined by integrating against e to the I and x's. Now let's do the same thing, but we integrate over minus infinity to infinity over the whole real line. F of x, e to the minus, and for convention, I'm going to think I want to put e to the minus 2 pi I x times c dx. So I'm just using the symbol c now instead of x, instead of end. And then if I think of c as being a real number, then f hat is now a function, now again another function from R to R, at least formally. Okay. So note f hat makes sense. This function makes sense if f is an L1, right? If I just take an L1 function on R or RD, then f hat makes sense, right? Because I can just put, you have to ask if this integral makes sense. This function just has as norm 1, so if I put absolute values inside the integral, I just get L1 norm of f. So in particular, this object is bounded by the L1 norm of f, of L1 norm of f uniformly in C. So here's our first theorem. Given f in L1 of R, let f hat of C to be defined as the minus integral from minus infinity to infinity f of x e to the minus. I'm going to have trouble sticking to my convention, 2 pi I x c dx. Then f hat from r to r is, in fact, it's not just a function, is uniformly continuous. And bounded on R. In particular, the L infinity norm is bounded by the L1 norm of F. The L infinity norm of F hat is bounded by the L1 norm of F. So we can make sense of the Fourier transform of an L1 function. This is called the Fourier transform of F. Okay, let's prove this theorem. So for continuity, we'll show that the limit as h goes to 0, f hat c plus h is equal to f hat of c. Okay, so let's just compute. Let's take this difference. This is equal to the absolute value, so e to the minus 2 pi I x times c plus h minus integral 2 pi I x dot c, which is equal to just combining the integral e to the minus 2 pi I x dot c times e to the minus 2 pi I h minus 1 times f of x dx. Okay, now, okay, so how do we proceed? So this an absolute value is equal to this. Now fix, okay, so where am I going to get smallness from? Where do I get smallness from? So if, on the one hand, I'm missing an x, sorry, this is important. So on the one hand, I suggestively written this that I can make this small. But where can I make this small? Well, I can only make when is this small? This is a point on the circle, and it's close to 1, right? If this argument is small, if this angle is small, right? Getting rid of the I, the e to the I theta, right? So if 2 pi h times x is small, well, h is small, right? I can make h small, right? But x might be very large, right? X goes so I have this problem with limits here, right? I'm making h small, but x is allowed to be very large. So x can go to plus or minus infinity. So I'm just going to chop this integral into 2 pieces. I'm going to just pick a big ball of radius r. I know I can, since f is an L1 function, I know its tail in L1 is small. So I'll just make the whole thing small by picking a big ball of radius r and it's small in the exterior, and then inside a fixed ball of radius r, I can make this thing as small, uniformly small, right? So fix r bigger than 0, large enough so that integral x bigger than r is smaller than epsilon. And then choose h small enough so that e to the minus 2 pi I h x minus 1 is less than epsilon for every x less than or equal to r, uniformly in x less than or equal to r. And so the above, this whole thing, is less than or equal to epsilon times the norm of the size of f inside the ball of radius r, which is just finite, plus which is less than or equal to epsilon times the L1 norm of f plus epsilon. So that takes care of continuity. For every epsilon bigger than 0, I can find h small enough so that this thing is smaller than epsilon. And for boundedness, and note that that nothing in this argument depended on c, right? This is I can choose my h uniformly in c. Boundedness is just that f hat of c is less than or equal to putting the absolute value inside the integral. This is less than or equal to f norm 1 since this thing has norm 1. This factor has norm 1. Okay, so so what this theorem tells us is that the Fourier transform makes sense as an object. It's continuous in L1, so it's a continuous mapping from, or it's a mapping from L1 into the continuous functions, right? How about this question of recovering f from f hat? Right, an analogy to what we did, well, the question that we spent so much time studying for Fourier series, right? When does knowing the Fourier coefficients of a function tell us what the allow us to recover the function? When can we recover a function from its Fourier coefficients? How about now? Can we recover f from its Fourier transform? So the formal analogy to Fourier series would just be writing f of x as being the sum over all the Fourier coefficients, right? But here, this is we're in the continuous land. So this we integrate fxc times e to the 2 pi I x dot c dx. Right, this is this formal object is the direct analog of trying to write f as its sum of its Fourier coefficients times these basis elements. But for the Fourier transform, since f hat is another function, this is typically called the inversion formula. So our Fourier inversion. I said Fourier, I meant to write formula. Inversion formula for Fourier transform it's called the inversion formula. And we can prove the following theorem. this is this theorem is let me write it down first. So if f is in L1 of R, and f hat is in L1 of R, then f of x is equal to as L1 functions. All right, so this is the exact analog of the first formula we proved, the first theorem we proved about Fourier series, right? If we have absolute summability of the Fourier coefficients, then we have uniform convergence. So right, let me go back to that theorem I wrote in the first page. So f hat being in L, if f hat is in L1, if both these objects are in L1, then we have this. We need f to be in L1 to make sense of the Fourier transform, but then to do the inversion formula, and at least in this setting, we'll try to refine this theorem a bit. F hat is in, if we assume f hat is in L1, then we can recover. This is the analog of this theorem. Right, we started off with L1t function. We had to assume that, maybe I should write this as f hat in A, meaning we had absolute summability of the Fourier coefficients. This is like this, and with this is little L1 summability, right? So we have summability. This is like requiring that the function be in L1, right? This is a discrete version of that. Then we can write f of x is equal to, we can recover f from its Fourier coefficients. So we have, this is an inversion formula for Fourier series. It's typically not called that, just from classical like terminology is this asking question of convergence. When does this thing converge and in what sense? But it's a direct analog of this inversion theorem.
And Professor, that holds pointwise everywhere or almost everywhere?
This formula?
Yeah.
It in fact, so okay, so f is an L1 function, right? So L1 functions we can only make sense of up to equivalence classes. So yeah, I guess this is the this would be almost everywhere. Correct. But then it's a little like, I think we typically don't write almost everywhere here, because we only discuss L1 functions up to being equivalence classes anyway. So if we understand that L1 being an L1 function means that you're just an element of a representative of equivalence class, then we just can write equals here. But yeah, yes, exactly. But but you're correct, right? We can't expect to take an integral and recover anything except in almost everywhere information, right? Yeah.
I was remembering a decaying condition like 1 over 1 plus x square.
Yeah. So different hypotheses under which this theorem holds, right? So this is one version of the theorem, and this is not the strongest version of the theorem. Just like this, the theorem that we proved for Fourier series was not the strongest theorem for which we obtain uniform convergence. Remember, we only needed C alpha for alpha bigger than 0 to get uniform convergence. So you're right. What's really going on here is that we'll need some decay hypothesis for f and for f hat for this to hold. So and L1 itself is strong. Later, in fact, this so L1 is in fact a bit of an awkward setting for the Fourier transform as well. L2 is again going to be more natural, and we'll show that in fact mapping, taking f and setting it f is to its Fourier transform is a isomorph, is a map from a bijection between L2 and L2. So yeah, there's various different ways you can formulate this. This is one of them, and it's requiring a lot. It's requiring that both functions be in L1. Okay. So before the proof is a little bit lengthy of the inversion formula. I think I'll do it next time. There's different proofs of it, all amounting to basically the same thing. But one question before we prove the theorem, and just backing up, following, Serdar's point. And yes, I just saw, sorry about the syncing the Dropbox file. The Dropbox file should be syncing. One question is, for which f do we have, for which f in L1 do we have f hat in L1 as well? Remember, the theorem we proved for Fourier series wasn't not necessarily super useful, right? Because it was hard to just take a that's why we spent so much time trying to understand it further and finding classes of functions for which we knew the inversion formula held, or for which we had uniform convergence. Just in general, if you give me a function, an L1 function, it's very hard to see if the Fourier transform is in L1. And let me give you an example, and it's not at all guaranteed. So in general, this is not preserved by the Fourier transform. So L1ness is not preserved. And let's write down an example. So an example, and let me just show you how useless, in fact, this formulation is in practice. Let's well, not useless, but instructive. I guess the examples that I'll write down are instructive. So what we're gonna do is tie back into this theme from before about smoothness and decay, this relationship between smoothness on one side and decay on the other side. So smoothness of the function is going to be related to decay of the Fourier transform. So in our setting now, this will be integrability of the Fourier transform. So, but I'm going to write down a very benign L1 function, just the indicator function on the interval of unit length. So f of x is just equal to 1. 1 here and 0 everywhere else. So this is an L1 of R, right? It just is, it has unit mass in L1. But what's its Fourier transform? So f hat of c is equal to, well, it's just supported on 1/2 to 1/2, minus 1/2 to 1/2, and it's e to the minus 2 pi I dx. Well, I know how to integrate this function. This is d by dx 1 over minus 1 over 2 pi I times c of e to the minus 2 pi I x dot c dx. And so this is just this function evaluate the endpoints. Minus 1/2, 1/2. And if I do this is just 1 over 2 pi I e to the I pi c minus e to the negative I pi c. Sorry, I forgot c here. Which is just equal to sine of pi c over pi c. And I'll claim without proof, I'll leave it an exercise, that sine is not in L1 of R with the and the C variables. Okay, so in particular, this decay is like 1 over Xc, right? So we know this is there. Okay, decay is like 1 over Xc. The hope would be that there's oscillation here, but it's this is not an L1 function. So in particular, once I put absolute values around this thing, I'm dead. Yeah. Okay. So in particular, if I start with L1 functions and take a Fourier transform, I'm not going to get an L1 function back again. So how do we? So maybe the question is, what else can I assume about the function f to ensure that f hat is in L1 and this inversion formula holds? And so we'll get into that a bunch next time. Sorry, I may have made a mistake with the computation. I'm seeing from the chat. Did I make a mistake in my computation or?
No. Yeah.
Oh no, you're fine.
Okay.
I just wanted to. I think that it has a special name. That function.
Yes, I'm seeing this. Yeah, this is called the sync function.
Even though sometimes in the textbook there might not be pi, but that doesn't really matter.
Yeah. Up to maybe if I had what I could do to fix that is if I make this interval, if I like to get rid of the pi, I can make this 1 over 2 pi to 1/2 pi. Get rid of the pi's everywhere. And then take 1 over pi of everything or something like that too. Yeah. But okay, in particular, this function you can do it by hand. But this is not an L1 function. So next time we'll see that if I require some smoothness so the thing that breaks here, the thing that's bad is that this function has this lack of smoothness. And once we start adding smoothness, then we're going to get decay of the Fourier transform. And we'll make that explicit next time.
I have a last quick question for you.
Yeah.
I thought there was this. Maybe I was looking somewhere, but isn't there a requirement of something to be in L1 and L2? Is that kind of where we're getting maybe with?
Yeah. So you can. So if I ask for f in L1 intersect L2 or something like that.
Yeah.
So yeah, there's various different ways of ensuring this, but yeah, I think this might be one way. If I also so asking it to be in L2. Wait, no, that's not good enough because this function is in L2 as well.
Oh yeah.
The inversion formula is so the nice setting for the Fourier transform is going to again be L2, and what we'll show is that this complex infinity functions are dense everywhere, are dense in L2 as we know, and we'll refine this understanding. I just wanted to emphasize that this is an awkward requirement, as stated.
I mean, your example kind of disproves that any LP functions.
Yes.
Doesn't really.
Yeah, this is. I mean, what the problem is the lack of smoothness. Is I need to additionally require some smoothness here if I want like this to be an L1.
Yeah, I guess one way to impose the smoothness is to make the derivative in some sense also integrable. That leads to the Sobolev space, but then
yeah. So or in fact L2 will be enough. So L2 so the hard thing is getting f hat in L1. But if I take L2 function, then this Fourier transform is an L2 function. In fact, it's an isometry between L2. So it's the hard thing is making this land in L1, and that's just not going to happen for any for just taking f and any just taking an LP function, like you say. I need to know more, like you say. So if I knew, for example, that the derivative of the function is in some integral space, then I'm in business. But that's like I said, that's requiring some additional regularity of the function, additional smoothness of the function.
Yeah.
Right. Yeah. So the point, the discussion will be quite enough. Like you guys should be it'll be a little bit of review, but this is going to be similar to the discussion we had about Fourier series. The same type of considerations we're going to make. So the additional once we ask for a little bit more smoothness, then we're going to be okay. Okay, guys. I also have office hours in a couple minutes, so I'll stop the discussion here. But if anyone wants to keep chatting, we can do that in office hours.
Yeah, sure.
Thank you.
Thanks, guys.
Thank you.
Thank you.
Thanks.
Thank you.
Thank you.
Thank you. Bye bye.
Bye bye.